Okay, so let's talk about the answers for the homework quiz. So the first one, mercury is a metal, right? Where is it on the periodic table? It's a transition metal, right? It's in the D block, which means it's filling the D subshell. The D subshell, they're orbits that are kind of barbell shaped. They go like this. There's one like that. There's one that goes like this. There's one that comes in and out like that. They're dumbbell shaped. They're very far away from the nucleus. And all of these materials, all of these metals in the D block in the center of the periodic table, they lose electrons to try to get to noble gas structure. Right? The problem is when you're in the middle of the periodic table, there's so many electrons to lose, it's really not practical to get to noble gas structure. So they don't have a fixed oxidation state. They don't have a fixed number of electrons that they tend to lose. Sometimes they lose 2, sometimes they lose 4, and so on. So the only way for me to figure out what the oxidation state of mercury is in this equation is to infer it, to use logic to determine what that oxidation state is in that formula. So you guys know that we start with the oxidation states, we're writing a new formula, and we crisscross them, right? So for example, if I had something very simple like, say, carbon bonded to oxygen, what's the oxidation state of oxygen? 2 minus, right? And carbon, in this case, 4 plus, right? 4 plus. Whatever goes out front is the cation. It's the positive ion. That's always the case. We always write that first. And when we name things, we say the cation's name first, right? The second thing is the anion, the negative charged ion. That's always second, and we always say it second in the name, right? All I do with these oxidation states is I crisscross them. That tells me how many oxygens I need. So how many do I need? 4. And how many carbons do I need? 2. You got to be careful not to, you have to be careful to actually divide through. If you can, you divide through. It's just like algebra, right? We want it to be the lowest possible ratio here. So this is a 2 to 4 ratio, which is another way of saying 1 to 2. Exactly. So we can just take those away and write. You get CO2, which you're very familiar with. What's the name of this thing? Carbon dioxide. All right. So that's how you use oxidation states to determine the formula. So look over here. Chlorine, there's 2 of these guys. Where'd that number come from? Why do you need 2 chlorines here to bond with that mercury? Because it's a 2 plus ion. Very nice. It's a 2 plus ion. So when you make a new formula with mercury on the other side, you're going to use the same oxidation state. So let's think about what the products will be. This mercury, because it's a metal, is going to replace what? Hydrogen or sulfur?
Hydrogen.
Hydrogen. Very nice. Because hydrogen's a metal, right? It reacts like a metal anyway. And in fact, at Cambridge, they just synthesized metallic hydrogen. So it reacts like a metal. It acts like it. So mercury is going to replace another metal. They react the same way. That's why it's doing it. It wouldn't ever replace a non-metal because they don't even react in the same way. That would be weird, right? That'd be totally weird.
Say weird again?
It'd be wicked weird, right? So what are the products we're looking at? What do we got for products? Hydrogen, what? Hydrogen chloride, what's the other name for that? Is this an acid? It is because the cation is hydrogen. What do we call it? This is a binary acid, right? There's no oxygen in it. Hydrochloric, very nice. What's the other product? Sulfide, right? Not sulfate. Sulfate is SO4. This is just sulfide. All right. So this is a 2 minus oxidation state, and this is a 2 plus. So what do I write? Nothing, because if I need 2 of these and I need 2 of those, that's a 1-to-1 ratio. So if I wanted to, I could write 1-to-1, but again, we don't tend to write ones in. So we would just leave it completely blank. The finished formula is just as it's written, HGS. And same thing for hydrochloric, right? Chlorine is a 1 minus oxidation state, so you'd need how many hydrogens? 1. And hydrogen's a +1, so how many chlorines? 1. So you don't write anything, you just leave it the way it is, like that. All right? Cool. So now our only job, and this is the most important job. All right. So if you got to this point, you're getting partial credit. I'll give you partial credit for writing the correct formula. But the most important piece of this is to predict whether or not this reaction is going to take place at all. This is not a single replacement. So this isn't just about which metal is more reactive. That's not how you predict this. How do I predict whether or not this is going to occur? The phase, right? If the phase changes, you get a reaction. So we're starting out with aqueous. Aqueous is our chlorides. The question is, are chlorides soluble? They are. The only exceptions are mercury, lead, silver. So this is soluble. What would I write down for the phase? AQ for aqueous, right? Aqueous means dissolved in water. Sulfides, are sulfides soluble? They're not. And again, we're using that chart on your periodic table right here. And we're just searching for sulfides. So use the anions, the second thing in the formula, to determine whether it's soluble or not. Sulfides are not soluble. Any exceptions?
NH4.
Yeah. What's NH4 called? NH4 plus. It's a polyatomic ion. What's it called? Ammonium. What's ammonia? What's the formula for that? NH3. Really good. Yeah. So, right, he's like, yeah, shocked. I'm shocked too. So, where was I going with that? Okay, sulfides. Sulfides are not soluble. The only exceptions would be if it was a group 1 metal, because they tend to be very soluble. So anything bonded to a group 1 metal is going to tend to be soluble. Or anything bonded to ammonia. So you already know this is going to be soluble, right? Because it's bonded to ammonia, and ammonia is very soluble. Making sense? So this guy right here, sulfides are generally insoluble, and this is not an exception to the rule. So what would I put down for its phase? Solid. S for solid, not for soluble.
Yeah.
Okay? That's the important distinction. So on your periodic table, I would highly recommend that in this box, that says soluble, you write AQ. That's going to be the phase, right? And over here in this box that says insoluble, you're going to write S to remind you that will be the phase. All right? Good. The second one, let's do this a little quicker. I'm not gonna labor over the formula like last time. What's strontium going to replace? Ammonia, right? Because that's the cation. It's a cation replacing a cation. Ammonia is going to take strontium's place. So what are the two products I have?
Ammonium bromide.
I'm going to have ammonium bromide. I'm not going to write that 2 there because I have to figure out what the new formula is with the oxidation state. What's the charge on ammonium? +1. So how many bromides do I need? 1. What's the charge on bromine? It's just a -1, right? So how many ammonias do I need?
1.
So I'm not going to write anything, right? This is a finished formula right here. And then what's the other product? Strontium. What do we call this? What's CO3? Carbonate. Carbonate has a 2- oxidation state, so I need 2 strontiums. Strontium has a 2+ oxidation state, so I need 2 carbonates. Do I write anything? No. 2 to 2 is 1 to 1. We don't write anything. It's finished. Are carbonates soluble?
Yes.
They're not soluble.
No.
Not soluble. The only exceptions being, read your table. What does it say? Exceptions to carbonate? What? Ammonium. Again, anything bonded to ammonium, because ammonium is so soluble, is going to be soluble. In this case, this carbonate is not bonded to ammonium, so it's not soluble. So I write what for the phase? I write S for solid. All right. And what about bromines? Are they soluble? Bromides?
Yeah.
They are soluble. Only exceptions being mercury, lead, silver. So this one's soluble. What do I write for the phase? AQ. All right, that's the homework quiz. Everybody on the same page, hopefully? Okay. So here's, we're just going to do a little mini lab. Here's the formula. Here are the reactants, right? Remember, this is called the reactant side. Each of these are called reactants. Your job is to just perform the reaction. This is Epsom salt, right? You can buy it at CVS. People
use it.
Yeah, people use this all the time. In the bath, right. And then this you would not use in the bath.
Why?
Because it's a strong base, all right? This is a strong base. If you use this in the bath, it would kill you. So here's something I need you to say after me. Ready? I need you to say, do what you oughta at acid to water. Say that for me.
Water to acid to water.
Do what you oughta at acid to water. Say it again.
Do what you oughta at acid to water.
Very nice. Okay. So here's why. All right. Here's why. If you were to acid or base, if you were to add that to water, it's a very exothermic process. It creates a lot of heat. If I were to pour all these crystals into a beaker and then add a little bit of water, it would get so hot that it would splatter at me. And splattering, obviously, with this is bad because now you've got acid or base all over your face, right? And then you'd look funny. And I don't want that for you, okay? I think you're all beautiful people. I want you to remain beautiful people.
Just looking at you,
Okay.
that's enough to realize.
Yeah, exactly. I mean, I'm pretty fond of my face, so. Here's the thing. You add this to water, right? That allows the reaction to happen more slowly. You add one crystal at a time and stir. It happens slowly. It's controlled. Does that make sense? If you add water to this, it will sputter at you. Okay? Do what you oughta at acid to water. Cool. You'll find next to the scales, there's stock material. You're going to add that stock to a beaker, tare it and weigh it, get the correct masses, and then create solutions and mix them. Is that too much? Okay. Don't wing it. This is on, the instructions are very carefully laid out right here. Okay, so follow them carefully. And the key is to write the balanced equation for that. If you want help when you go home, like if we don't finish this in class, refer to page 301 in your text. Okay? Making sense? Questions? Notes for today and a video for today will be posted online if you want to review something. There's also notes and a video from yesterday's class on Classroom, okay? Go for it. Head to the back.